As we go through this today, if anyone wants to follow along a little more hands-on, a lot of the content we're going to be presenting is more in depth in the documentation here, and there are also notebooks that follow along with all of that. So if you prefer to be a little more hands-on, you can take a look, go to that link, and in the notebooks folder, there should be Jupyter notebooks that have a lot of the content we're going to be presenting today.
And I think we'll get started. I think that was a great way to get started, Ryan. So my name is Kishore Iyer. I'm here with Ryan Soley, who's the lead maintainer and developer of rubicon-ml. It's an open source library, a Python library for logging and metadata tracking focused on machine learning models. But it could be more generically used as well. The target use case right now, though, is for machine learning models. I'll start out, this tells us a little bit about us. We are from Capital One's Machine Learning Experience, or MLX, organization. It's a multidisciplinary team focused on creating and standardizing tools, predominantly software that's used in-house, and approaches as well in terms of workflows to power the machine learning efforts of associates across Capital One. Both of us are based out of the New York City office, but we are here all day today, so feel free to come talk to us. So I'll start out by the problem that we are trying to solve. So building a machine learning or an ML model is an iterative and actually an experimental process. So you typically start out with some data. You pick out some features that you like from the data or that seem to be relevant, and then you pick out a modeling technique, and typically modeling techniques have parameters associated with them, which are called hyperparameters. So you train with some choices of hyperparameters, and you get to your first model, but then you may realize that maybe this isn't the right modeling technique, maybe this isn't the right set of features, maybe this isn't the right set of hyperparameters. So you got to go through this flywheel, typically more than once, even if you are a fairly experienced modeler. And as you do this, you want to, as a good engineer, as a good developer, you want to keep track of this information. And old school, you could write it down in a notebook. You could save it in Google Spreadsheets or Google Drive. But all of those are manual techniques. What if you could automate the process, right? And as you're modeling, there is some tool that is basically keeping track of this information in a way that is accessible. So this is the problem that we're trying to solve. And these are all the reasons why it is important to developers and stakeholders. When leveraging machine learning to make business decisions, tracking experimentation is essential to ensure reproducibility and auditability. You'll probably be doing this over a period of time, building models, and you may not remember. It's important to remember the details. You want to go back in time and see what you did maybe a month back, a year back. In the line of business that Capital One is in, the models that we build, we have to also mitigate risk. It's a very important aspect of the models that we build. And so it's important to know how exactly the models were built. And so we want to track that information. This, I believe, is fairly common for organizations in the financial industry or in any regulated field. Generally speaking, mitigating risk is fairly important. And you also want to enable thoughtful and responsible modeling. Like I mentioned before, as an engineer, as a developer, as a scientist who's doing this, you want to track this information in an automated manner. Now, when you set about trying to solve this problem, you realize that it's a fairly nuanced problem if you start writing code for it. There are, there's this very common Python library called Logger that you can use to log information. If you've ever written code in Python and you start not liking your print statements, you'll start using Logger fairly quickly. But then as you start going down this track to say that, hey, I want to log the information that I'm building my models with, you realize that there's a lack of standardized tooling and many ad hoc solutions that have that can come up fairly quickly. You have competing technical priorities, making it hard to prioritize experiment tracking. This is a big one. So when you're building a model, and we see this fairly commonly with modeling and data science teams, that you want to get the model out you want to, and that may mean different things at different points in time in the model development lifecycle. For example, if you're in the process of tuning your hyperparameters, that becomes the most important thing that you're doing and takes up a lot of bandwidth. So if someone comes and says that, hey, are you logging and tracking the metadata around the hyperparameters? Yeah, we are doing our best, kind of is not an uncommon response, and it's an understandable response because the focus of the data science teams at that point in time is that particular task in the process of building the model. And their primary goal is to get the model out by a certain date typically. So that is what we mean by competing technical priorities. Many times logging and metadata tracking or experiment tracking can take a backseat to some of these more critical items. The third aspect that makes this not trivial is existing solutions tend to require dedicated infrastructure. So we have seen solutions in the available that will basically say, yeah, sure, we can do your metadata tracking, we can do your logging. All you need to do is set up this server. And that becomes a non-starter for a lot of data science teams. Typically, these are folks that are focused on data science and may not have the engineering expertise needed or the bandwidth needed to set up dedicated infrastructure. Do they need a server? Do they need a container? Do they need a cloud API service that they need to connect with? All of these become non-starters in cases that we have seen. And finally, this is writing experiment tracking code in rapidly changing machine learning database code bases, right? The code bases are rapidly changing, and there are so many different libraries that are coming up that you need to incorporate. And so how are you going to keep track of the code that you are trying to instrument in some sense? So with that, I'm going to hand it off to Ryan Soley. To address these problems, we built an open source rubicon-ml to help, and Ryan is going to tell you all about it. But before that, we have Tyrell, who has an important announcement here.
Hey, thank you for this commercial break. Hey, my name is Tyrell James. I'm just here to tell you, if you are playing the game, the code for the game is feature 23. So if you are playing the game, the code for the game is feature 23. I believe it's all lowercase. Okay? If you have no idea what I'm talking about, don't worry about it. I'm just wandering around anyway. All right, thank you guys.
Thank you.
Thanks a lot, Tyrell.
All right.
Yeah, and you could potentially log that with rubicon-ml.
Oops, sorry. All right, thank you, Kishore. So as Kishore mentioned, my name is Ryan Soley. I've been working on Rubicon pretty much since I started at Capital One in about 2017, and Rubicon predates me by a bit at Capital One, maybe a year or two. For a little bit of historical context, before Rubicon was an open source Python library, it was a complete productionized internal solution. So basically within Capital One, there used to be the Rubicon server and the Rubicon UI that was fully hosted, as well as the Python logging library as the programmer's interface. And at that time in our journey at Capital One, our team was simply the Rubicon team, so we had the bandwidth to sustain all of that. But as we grew, we became the enterprise tooling team and needed to support many other tools. So we decided to remove the infrastructure burden from us. And not only did that make our lives easier, but it enabled us to easily open source the logging library with a variety of different backends. So throughout this talk today, I'm going to provide a high-level overview of Rubicon's core functionality, logging and visualization, pretty simple stuff. And then we're going to get into some of the new features that we've recently added, which contain things like logging to multiple backends at once, using schema to instrument logging of popular Python libraries, and to new ways to query our logged model metadata if we'd rather not use the Python library directly. All right, so as far as core capabilities go, Rubicon is not doing anything terribly difficult. As Kishore mentioned, this problem isn't hard because logging metadata is hard. It's hard really because it's easy and because all sorts of different teams can just do it real fast and have their solution ready to go and have something that works for them. But where that becomes difficult is when you're trying to review models. If two different teams from different sides of the company trained a random forest classifier but are logging wildly different metadata about it, a reviewer won't be able to easily compare those models, or in the future they need different processes for dealing with them. So in order to mitigate that, we've designed Rubicon-ML, and at the highest level, we organize Rubicon's metadata into this ontology here. So we have a project, and the project is generally a wrapper around all of the metadata you're going to log. Projects generally represent a model, but all of this is very freeform. As Kishore mentioned, you don't even need to use Rubicon for machine learning. It can basically be used to handle any iterative task. So for example, in the past, we've used Rubicon to just monitor API responses, things like that, and do performance testing types things as well. So the way we organize this data is within our projects we have experiments, and in the machine learning world, these experiments are generally runs of your model. If you're doing a grid search or a random feature selection or elimination, it's generally going to be the different iterations of that. And also at this top level, we have what we call artifacts and data frames, and these are generic, just binary catch-all data types that may relate to your whole, your project as a whole, summaries of the experiments, things like that. And then within the experiments, we have our more traditional, machine learning inputs and outputs that you may be familiar with, things like features and parameters and metrics that are all key value pairs, as well as, again, artifacts and data frames. So, you may have some artifacts and data frames that are specific to your particular experiments, and some that are specific to all of them together, and that's when you would log them at the project level. And what this looks like in a simple scikit-learn pipeline here is something like this. So this is manual instrumentation of Rubicon logging. And we're creating our Rubicon object up front, and we're simply providing a persistence and a root directory. Those are the only required inputs. So here we are just telling it to write directly to our file system. So here you can see this is kind of the first place where we've removed the server-based backend. Now we're simply writing these logs as JSON data to the file system. On the next couple slides, I'll show some other options that we have for logging. But once you've got your interface there, one other flag worth mentioning there is that auto get enabled. If you're logging Rubicon metadata from somewhere in your file structure where there's a .git directory at the root or somewhere in it, Rubicon will automatically pick up information like branch names, commit names, repo names, and things like that. And that's just so all that metadata can be associated to every project and experiment. So you don't need to log actual code to Rubicon, which is something that people did in the past, and we were like, yeah, let's stop doing that. So beyond that, we're creating a project and experiment and logging our features, parameters, and metrics. But here you can see in the manual case, this is all line by line. We're only logging the metrics and the inputs that we specified in our code block up top. So there's a lot of information that we're not quite capturing here. And again, I will touch a bit on that in some of the newer stuff later on in this presentation on how we can make that a bit more robust. And once this is basically what your file system is going to look like from this particular example. So Rubicon uses a nested hierarchy like this because our team at Capital One also works very heavily with distributed frameworks like Dask and Spark. So we wanted Rubicon to be able to write atomically so that in distributed environments there were never any issues with collisions and things like that. So that's why we chose to write Rubicon in a structure like this rather than more of a flat representation. Now, depending on the backend type that you configure, this may look slightly different, but for all the ones I'm going to focus on today, this is essentially what you would see if you were to take a look at the file system you're writing this data to. Okay, so beyond just the local system, we use a library, another open source library called fsspec, or file system specification, to handle writing to different backends. If you've ever used pandas or numpy or Dask, you've used fsspec before. It essentially just provides a bash-like interface with things like rm and cp to do various file system operations over different file systems. So we directly support and have testing for in-memory logging for experimental stuff, local logging like I showed before, and S3 logging. And all of that is directly supported out of the box. But if you're familiar with fsspec, or if you go take a look at their repo, you'll see that they have 20, maybe even more now, different backends that they support. And in theory, they should all be able to just be plugged right in and used. If you try to do that and find any problems, please open an issue. And beyond that, it is pretty simple to create custom backend implementations. So ultimately, in Rubicon's repository layer, there's a single function that is sending a JSON blob to a file system. So you can imagine that swapping that with maybe an API would be pretty straightforward. And in fact, we've done that in some cases to enable logging to more persistent storage. So what this looks like is simply changing the instantiation of your Rubicon object. So in this one, now we're logging in memory. So essentially what this is going to do is to just log all of these files right into your current Python session is memory, and as soon as you end that session, this will all go away. So this is great for when you're just practicing and getting started with Rubicon, or when you're trying to figure out what exactly you want to log for your model so you don't pollute your file system and have to clean up later. Then once you're ready for something a little more permanent, you can simply switch to the file system persistence here, and I'm just giving it the current working directory as the root dir, but that root directory can be anywhere on your system. If you're using a mounted file system, this will also work there. And as you can see, all we did was change the one line, and we can still create the project and experiment exactly the same. Same deal for S3, still file system persistence, but this time we just give it a root dir prepended with the S3 path, and FSSpec knows what to do with that and can handle everything. As far as access goes, so since FSSpec is using Boto under the core, all of that configuration is standard. If wherever you're logging from is already set up to interface with AWS, then this will work just fine. So essentially the goal here is, instead of having a custom backend or a server like we used to, now Rubicon is very plug and play wherever you may be. So it's easy to get up and get started no matter what platform you're on, no matter what system you're running on, or no matter where you want to log the data to. Okay, so after you've logged your data, of course, you're going to want to do stuff with it. And there are retrieval functions similar to all the loggers that do the opposite and just give you back the data, and then you can do with it whatever as you please. But we also have a handful of visualizations. And these visualizations are powered by Plotly and Dash, if you're familiar. So anything you can do with those, you can do with these. The visualizations can be hosted locally or run inline in a Jupyter notebook. And if you're well versed in Dash and Plotly, they can pretty easily be hosted on like a Docker container, in a Docker container or something like that. So what this looks like is very simply, we have a viz module that has a few classes in it. They can be simply imported and pass some experiments, and then you can serve visualizations like this on your local host. So what we have here is an experiment table, pretty straightforward, just the IDs of all of our experiments as well as the inputs and outputs, and we can sort, filter, compare, all that fun stuff. And also we have a link here out to GitHub, so since we enabled that auto git flag, that will take us directly to the commit that logged each of these experiments. This is just one of the visualizations in our suite. Here are a couple of the other ones. So in the top left here, we have a data frame plot. So if you log a data frame with a consistent schema to many experiments, you can plot them all together. The one on the top right is a metric correlation plot. So you can choose between different metrics to anchor this on, and it will show you how the different inputs affected them. And finally, down at the bottom is a list metric comparison thing, but more generically used for comparing coefficients, seeing how coefficients change throughout the iteration. All right, so that pretty much covers the basics of logging and visualizing your data. So today, now with the rest of this time, I'm going to get into some of the new features that we've added in the past year. A lot of this was through requests both internally and externally, a lot of features that we've been working on for quite a while, so we're excited to show this stuff today. So, as I already showed, we have a number of different backends, but the way we previously did it is, you would do one at a time, or if you wanted other ones, you would just need to repeat that code. Now, we have implemented what we call composite backends, so you can configure any arbitrary number of backends as you'd like. So this example here is a bit contrived. We're just logging to two separate local file systems, just a Rubicon root A and a Rubicon root B. Normally, you would probably do something where one is like local and one is in a more persistent storage. For example, like if you wanted to be able to quickly analyze a lot of data, you could log it locally and to S3, and those local logs are just going to be easier to retrieve and access than dealing with the network on S3. Additionally, like if you have a API-based service, like I mentioned is possible, you could log locally for yourself and to that for the enterprise or something like that. And pretty straightforward. We get two different root directories here just by one call to create project and log experiment. So now, by giving it this composite config, we can just with one simple call log to many backends at once. And that just reduces lines of code. A lot of the new additions here are in at the effort to reduce the lines of code needed to actually get Rubicon implemented in your code base efficiently. All right, so the next one, which is one of the very big additions recently, is the introduction of Rubicon schema. So our reviewers, our model risk office at Capital One, a lot of their feedback when it came to Rubicon was that it required a lot of instrumentation, and that it would be nice if it was easier to just get up and running with commonly used models right out of the box. So that is what we designed the schema for. So here we have an XGBoost classifier, which we use XGBoost quite a lot. And it's very commonly used across different teams for different tasks. But even if you're doing different things with XGBoost, it still has the same inputs and outputs, right? So if Team A is using it for risk stuff and Team B is using it across the company for auto finance, the models should still can still be compared because they are still XGBoost models. And the problem then arises when people manually instrument logging, like this block down at the bottom. So, if you could imagine two teams on different sides of the company like that, instrumenting this particular block of code differently, depending on what features, parameters, metrics they want to log, things like that. And if those two teams are doing those differently, then we kind of lose some of the value of this generic, standardized comparison. So we simply replaced all of that with schema logging. So now instead of all of those different log this, log that statements, we simply get a project and we can log our XGBoost classifier directly to that project. So under the hood here, the first thing log with schema is doing is inspecting the object that you passed in. So this, for this particular example, and if you are taking a look at the Rubicon code base, you'll see that the schema that we currently have are all for models that fit the Scikit-learn estimator specification. That's not a requirement. A schema can be developed for any old Python object. So if you have custom stuff that doesn't fit that standard, totally still usable. So when you call log with schema, we're going to infer that this is an XGBoost classifier by the library name and the class name, and pull the, I knew as soon as I touched that HDMI cord it was going to do that. There we go. All right. Okay, so you pass in an XGBoost classifier, and it's going to infer the schema. Now, what it's actually, you may notice this one, the name is XGBoost model. So what actually happened is we inferred the XGBoost classifier, and the XGBoost classifier simply just points to this schema since it's a pure superclass of it that has no additional features. So that's why we're going to take a look at this one. But basically what we see here is just some simple metadata up top, mainly defining the dependencies for this particular schema. And then the values that are defined in here are how you want to log different things to Rubicon by pulling them off of that object. So there's a few different ways that happens in artifacts here. So we have the self special keyword, which will log that XGBoost classifier directly to the experiment. We also have this function getter. So if you want to log something from, or the result of a function from your particular classifier or whatever object, you can use that. And the most generic one here is just this value attribute. So basically for this first metric here, we're saying that we want to log a metric named best iteration retrieved by doing XGBoost classifier dot best iteration. And this optional true here is just to say, like, this is an optional attribute on the XGBoost classifier. For example, if you for some reason were to try to log an unfit one, that metric wouldn't be there, that attribute wouldn't be there. So this just tells it that it's optional and not to error there. These schema are generally designed by just looking at the API specifications for these libraries. So like if you take a look at the XGBoost classifier docs that are linked here, it's going to look pretty much the same. They're designed to be very verbose and capture everything. So now if we take a step back here, we're now, right here we were logging 5 or 6 things with a bunch of lines of code, and now we're logging 30, 40 different parameters, metrics about our XGBoost classifier with just this one line of code. So yeah, basically these schema, we're very actively working on them right now. There's direct support for XGBoost and LightGBM within Rubicon, as well as some simple like toy Scikit-learn ones. If there's any other stuff that you're interested in, definitely feel free to open an issue or even contribute it yourself. They're pretty straightforward to make these, and there's a whole contribution guide in our documentation for adding schema. Other than making the YAML file here, it's just a few simple lines of code to register it with the library. And on that point, you actually, if you want to design schema that are like proprietary to wherever you may work, Rubicon can also register schema, without them actually being present in the library. So if you wanted to use something internally to model or to represent some kind of internal model that isn't publicly available, you can do it exactly the same way. All right, and finally, one of the last new features that we have here is for querying logged model metadata with a JSON path-like syntax. So originally, or in the most core way, like you can, if you're familiar with Python, you can interface with Rubicon up on the like how you're doing in the top left here. You can retrieve your experiments, metrics, etc. And just access the attributes of them that define things like names and values. So this is generally how other software developers that are implementing Rubicon would do it. But sometimes we found that there are less technical teams that want to retrieve and evaluate data within Rubicon. So we have started working on new ways to query this data. So this first one here is using JSON path-like syntax. There are a number of data teams that we've worked with that are more familiar with something like this than writing Python code. Now I know personally I would much rather just use the Python, but got to work with our users, and we're currently exploring like other querying languages that may be popular. This, just like a lot of the other stuff in Rubicon, is based on an open source library called JSON Path NG. We're pretty much funneling a lot of the work out to that. That's a big point of Rubicon in general. Rubicon is very, very lightweight. The majority of the actual work is being done by the open source libraries that we are depending on. For example, the file system writing via FSspec, the visualizations via Dash and Plotly. Essentially, we wanted this to be very lightweight and just provide a domain language on top of those things. All right, so with that, I believe that wraps up the content here, and we're very ahead of schedule. I'm surprised it went that quickly, but does anyone have any questions? We'll start there. If not, I could dive some more into some of this stuff if the questions lead us there. Go ahead. Not anything that I'm confident that we can share right now.
So basically, we are part of the enterprise ML tools team. So what we do as a team is to build software for data science teams across the enterprise. Now, Capital One is building hundreds of models, and there are many teams across the enterprise, and they are in different domains, right? So basically, what we do is to maintain the library, build the library, and make sure that it sees adoption internal to Capital One and hopefully externally as well. So long answer to your question. So we should talk, maybe take it offline. We have folks who can probably help you out even more. We're just a bunch of engineers. So are you part of a reporting organization, or are you a reporter, or? As a developer. Okay, sounds good. Yeah, we can talk. Yeah.
I saw a hand over here.
Question over there. Yeah.
Sorry.
Like integrate, so part of this is you're logging your experiment tracking over to whatever source you're choosing. So like memory, local system, S3, and you're generating, I guess, randomized UIDs to track each set of experiments. I saw one portion where you're also tracking that in Git as well. Are you doing something very similar to like DBC is doing there, where you're doing hashes of like the data output and then storing those hashes in Git, or is that
No, so nothing is actually being logged to Git via Rubicon. We're pulling information from GitHub via the Git CLI to log that information into Rubicon. So we're, when you pass that auto Git logging flag, essentially every time you create a project, it's going to pull the repo name and the URL of the repo that you're working with based on the .git folder, and for every experiment, it's going to log a branch name and a commit hash. So you can imagine, having multiple experiments for different branches, commits across a project. And then, like in the visualizations there, that's simply just a link straight back out to GitHub. So we're not trying to like reinvent any of that stuff.
Yeah, I was just trying to understand like how what you're doing compares to DBC. Like, and I understand you're working in a specific niche here, where you're looking at standardizing logging and how you're logging across a lot of enterprise situations. But like, I see and assume like somewhere getting later on down the pipeline, you might plug in DBC to like, okay, we've got all these experiments. Let me go and version this in a way that I can like compare later, or like in a more efficient way. I don't know.
Yeah, no, that makes a lot of sense. At the enterprise level, we haven't really gotten that deep into like users then retrieving tons of these logs yet. We're actively working with like a lot of teams to do that. So yeah, I don't have a great answer yet, but that's a problem we're aware of and currently tackling.
If you can get your teams to log at all, like you're probably doing well.
Do you all know how big like the external community use case is outside of Capital One? If it's a lot of use, or is it like?
Yeah, so I'll say for sure, like a lot of the contributions come from internal to Capital One at this current point. You know, we've got about 100 stars on GitHub, about like 80,000 downloads from Conda, but I don't know how accurate those really are with all the caching they do. But yeah, I would say currently it's definitely more so internal support, but we're hoping that with like the schema stuff that we can start, you know, encouraging other people to kind of log stuff or contribute in that way.
And just one other thing, have you considered doing something like, you may have something set up to have a standardized project. Are you doing any kind of cookie cutter template to get this set up or anything like that? It seems like it would just go naturally with this.
Yeah.
Yeah, so that's a great call out. We should catch up. All of those are good pointers. We generally tend to have a bunch of cookie cutters inside Capital One to do exactly what you're saying. So tying that up with something like this should be fairly easy to do. Where are you coming? Where are you coming from when you ask for that, or when you suggest that?
So like I kind of live on the other side of the house here, so you guys are doing more research tracking in the training area.
Hmm.
I am on the inference serving
Got it.
area.
Serving area.
So
Hmm.
like where I'm using cookie cutter is I'm prescribing out templates for my data scientists and my software engineers to start containerizing and serving models in open source solutions.
Hmm. Hmm.
And so that's the quickest way for me to do it and
I see.
have it be somewhat consistent.
Right. Right. Yeah.
Yeah, no, that makes a lot of sense. Yeah, I think like in a more abstract way, like the schema stuff is kind of a first step towards that, and but you're talking at like a higher level than that. Yeah, that's definitely
You take your current schema and throw it into a cookie cutter.
Right.
right. Exactly. Yeah.
Absolutely.
Yeah, and like sometimes for certain things, like we can like nest schema. So if we have like a grid search meta estimator and then something below it, that's like the main reason we made the inference stuff. So like, or that's the main reason we like incorporated all the inferring of the model object. So you don't need to like know what's coming and set it beforehand if you want to incorporate it into something more generic like that.
That's good. Like a lot of stuff in the open source system like this has to kind of bring your own house, right?
Mm-hmm.
The piece that you want.
Hmm. 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 Yeah. Yes.
Can you explain when I would use the in-memory capability versus just logging into a file?
Yeah, sure. I mean, if generally like I use the in-memory stuff when I'm like just getting started with a new project and like I don't really even know what I'm trying to log yet or like what it's going to look like. So yeah, but that versus file system is really just a preference thing. Like if you're working like purely locally, then yeah, they're probably going to be not very like the speed difference is going to be negligible. But we like do a lot of logging on platforms to like mounted local file systems, so that can be a bit slower. So you know, just things like that. But generally, you know, the memory one is very ad hoc, and if you're comfortable with using the file system, yeah, you probably wouldn't really use it much.
So follow-up on that is, so there's a lot of basically Python 101s, 201s that basically say don't use print, use logs.
Hmm.
How do I get the data out of the memory so I can see it, like not printing it or something like that?
Right, yeah, so the Rubicon, like the retrieval methods, like here, if you're using the Python library to retrieve data, you would just need to do it like that, but that's with the caveat that if your Python session ends, that data goes away since it's in memory.
Right. So speed would be one reason why you would want to use memory. You know that for a fact that you'll not have persistence. You can lose the data, but you're okay with it, right? Because like he said, you're just trying things out. You know, you want to do it quickly. And with file systems, yeah, I mean.
Yeah, you definitely wouldn't find yourself using the memory in any like production workflow or anything like that.
Yeah, absolutely. In fact, you might want to use the S3 or something like that even there, right? But you will pay a cost in terms of speed, right? Memory is the fastest, so yeah, sure.
Maybe for validation and testing.
Right?
Yeah.
Absolutely.
Like if you're running a CI/CD pipeline validation testing, logging the memory and comparing to something would be faster.
Yeah.
Yep, yeah, anywhere where you're using some kind of like ephemeral
Yeah.
thing that's going to disappear anyway.
Yeah. Another example that may be the case is that if you're using schema, for example, and you have like, you know, you have a schema for the XGBoost model, for example, it has maybe 50 parameters, 40 parameters, and you don't know which one should be optional, which one shouldn't be, etc. Right? So you can try it out in memory, probably see what the output looks like, and then as you see it, you might be like, okay, I need only 15 of these. I don't need the others, so I'm going to set them to optional. Things like that. You can iterate over it. A lot of this process is iterative, so you can iterate over things like that. But you do it in memory because you don't want to. The other stuff is going to take you slightly longer. So.
Yeah, we're trying to toe the line of being, you know, prescriptive to the point where we can like compare these models, but still flexible enough to allow users to, you know, do what they want without a lot of guardrails.
Yeah, nothing but questions.
Go for it.
I can defer, but like, so looking at what you're looking at as far as like reading and writing out the file system versus memory, do you have a concept that like you're running something, and maybe this is way scope creep in another direction, having sort of a batch write to files. So if you're running something extremely big, you're logging it first in memory, and then after a while you're dumping that to a file versus scope creep, something like that.
Yep, yeah, we've talked about that a lot. We have yet to find ourselves like a use case that gave us, you know, the priority to actually look further into it. But yes, it's something that we definitely are considering and are thinking about, especially with the schema now. Like people are going to be logging more and more with how, you know, verbose those can be.
Yeah, I wonder if Linux file system caching may also help you there, because generally speaking, the operating system itself will log to memory and then push it to disk, etc. So you'll have some of those optimizations that may come in for free, whether it's rubicon-ml or whether it's, you know, you just writing a big.
Yeah, or that's a good point. And in file system specification, I believe there's a degree of caching as well. I think, I don't know what the syntax is off the top of my head, but I think there's a way to like prepend your strings that you pass through to FS spec to tell them to like cache first. But yeah, we could definitely look into more first class support of something like that, because you're not the first person that's asked something like that.
And I wonder if do you guys have any logging support to log out to like Kafka?
So like I mentioned, like it's pretty straightforward to write backends for Rubicon. So essentially, like if you were to look at the code base, there's 3 layers to it. There's our domain layer that's just like defining project, experiment, whatever. There's the client that's doing the writing, and then we have a repository class. Or, I'm sorry, there's a client that's dealing with the user input, and then we have a repository class that's writing things. So those repository classes can be easily like rewritten and pluggable to write to different things. And as I mentioned, we're just writing JSON blobs. So if you're sending it to an API, you'll just need to, you know, reconfigure it a bit.
That's fair. I'm going way deeper.
No, it's great.
These are all good issues. Yeah.
Yeah, thanks for keeping the conversation going. I ended earlier than I thought.
Yeah. If you have use cases for this, we would love to hear about it, and yeah, create issues, and we can go from there.
We could chat.
So, just putting those two together, so what I'm seeing here is, so first of all, JSON path is the new way of being able to do it. So if I had an inventory object, then I could
Yep.
do a search with the query.
Yeah.
That's really where you could tone down how much you're spitting out.
Right, definitely. Definitely.
So is the JSON path querying, are most log managers now wanting that? So are you embracing that because it's a demand?
I mean, I wouldn't say it was like it was an ask for sure, but I don't, like it's not an ask that we've gotten like a ton. It was just something that was pretty easy to implement, and it was, you know, it was an easy win for us, so we just went for it. But we designed it in a way that like it should be pretty straightforward to support other querying languages. So like if there is a particular, you know, if there's a particular one that you're familiar with that you think could plug in nicely, it should be pretty straightforward.
This is new for me, so I'm just like the GraphQL world.
Okay.
There's no standardized querying.
Yeah, I wouldn't call this a standard.
Is it going to become?
Probably not. Like in my experience, like the JSON path stuff, like to me, I feel like is kind of old. Like I said when we did this, like I probably wouldn't do it that way. But like it's been more of an ask from like the data science side and like the analyst side rather than like the software side.
Yeah, and to go back to your question, I was just thinking about it, how much time that it has saved. We'll have to go back and check, but generally speaking, we are seeing broad adoption across Capital One for this in terms of modeling teams taking this on, because this is a problem, like I said in the initial set of slides, that you're focused on building the model, you have something to get out, that's your primary objective, but you have to do logging as well, and you want to do it in a systematic, orderly manner and you want a lightweight tool to do it that integrates well. So when we come in, generally speaking, it's an easy sell because the only other thing that people are fairly familiar with is print or logger, for example, right? There are other tools, I'm not naming them, but ours is pretty competitive in the big scheme of things, and it has certain, the lightweight aspect of it, the fact that it doesn't have require you to set up a server, all of those tend to appeal to folks, even if it's like, hey, I can quickly try it out. You can quickly try it out. One of the things that I think we can spend, like we can at least flash it, is the GitHub repo. We have a ton of examples, tutorials, notebooks, all of that stuff. So if you want to get started with it, it's all out there and it's all open.
Yeah, so here's our repo here, GitHub, capital1.com, or I'm sorry, capital1/rubicon-ml. So if you take a look at our documentation here, all of these examples on the left here are generated from Jupyter Notebooks in this notebooks folder right here. So if you want to, you can just take a look through the documentation itself, of course, to see how to do these things. But if you're also interested in running through this all yourself, it's all right here in this notebook. So all the documentation is pretty interactive.
Yeah.
Can you kind of talk through, like, I guess, a typical workflow that you would use? Because, like, I see it's like, so is this generally a pretty linear process? Like, oh, experiment, do you like recording every experiment you do, or are you really like, I want to record, here's the 15 times of boostses, and then there's
Right.
things that I want to export, or like, how does the usual work?
Yeah, so generally we're very just like throw everything at Rubicon, log it all just so it's there, and then kind of deal with that part on like the retrieval end. And one of the ways that we facilitate that, which I should have talked more about and totally forgot about, is that like every entity within Rubicon, if we go back to this slide, everything in here can just be arbitrarily tagged with like string values. So, you can tag things best, worst, good, bad, whatever. And yeah. Oh, or both. You can, if there's some way you can determine that up front before you log your experiment, you can push it in, or you can log it after the fact. So you can do it either way. And then all of these retrieval statements, like this one up in the top left, like the metric where we're giving it the name, you could also, instead of name, give it tags and get all the metrics with that particular tag.
And should we show them the flywheel? Generally speaking, from a process perspective, you were asking about the workflow, right? So this is, generally speaking, we are just following the model development lifecycle, but this is not the only way you need to do it, right? The last thing that I should say that we are seeing slowly happen is that we have talked about gradient boosted tree ensembles and specific kinds of models, but you can use it with linear regression models. You can use it with logistic regression models. You can use it with neural nets. You can use it with transformers. It doesn't really matter. At the end of the day, this is agnostic to all of that. So that's one of the selling points of the rubicon-ml, that it really does not, the model does not matter. It's not tied to it, right? It's at the end of the day a Python class that you need to interpret or infer so as to potentially create a schema, or so you can always take the examples that are there for XGBoost and correspondingly apply them to, say, PyTorch neural net. You can do that. So.
Cool. Well, with that, I think we're at time. But if anyone else has any additional questions, please feel free to come up and ask us. Yeah, thank you so much for joining us today, and thanks for all the questions.
Yeah.